Well, this is lecture 24 of Basic Calculus 1. So, today we will be discussing an important notion which helps in evaluating the limits of certain forms using the derivatives. So, it looks a bit of the place because you define derivatives through the limits, but we are telling that we will be evaluating the limits through the derivatives. Okay, but it is not applicable everywhere. It is applicable in certain forms when the functions for which you want to compute the limit are in certain forms. So, that is called L'Hopital's rules. We will look at them now. Okay, just to start, let us look at evaluating this limit, that is limit of x square plus x minus 2 divided by x minus 1 as x approaches 1. So, here as you know, if you have a function of the form f x by g x and limit g x is not equal to 0, you can take the limit separately, that will be equal to limit of f x divided by limit of g x. But here that is not applicable because the denominator x minus 1 has limit 0 when x goes to 1. So, that is what we say intuitively, that we cannot just substitute x equal to 1 here. But note that when the denominator becomes 0 for x equal to 1, the numerator also becomes 0 here. It is just 1 plus 1 minus 2 which is equal to 0. So, this is something called 0 by 0 form. Okay. So, for this we note that we cannot just substitute x equal to 1, means we cannot take this limit separately and divide by. But you see from the numerator that numerator is x minus 1 into x plus 2, right. You have x minus 1 into x plus 2, that is x square plus 2 minus 1. So, that is plus x minus 2, that is what the numerator is. So, we can really cancel this x minus 1 from denominator and numerator. So, you get the numerator as x plus 2 only, the whole ratio is x plus 2. Now, you can take the limit and that will be equal to 3 of course. So, this we used to do everywhere else. But look at the definition of derivative also. So, in the definition, say derivative at x equal to a is equal to limit h goes to 0 of the ratio f of a plus h minus f of a divided by h. Here you see that if we take anything near h near 0, h near 0, the denominator goes 0, numerator also becomes 0, right. So, it is again in the same 0 by 0 form. Any derivative, definition of any function you take and the definition of that derivative would give rise to this limit. That is again we cannot just substitute h equal to 0 there. And it is not also obvious here, like whether that h can be factored from a plus f of a plus h minus f of a as in the previous case. We do not know how to factor and cancel this h and then take the limit. That is a problem here, right. But then we can see something else. Suppose we differentiate the numerator independently and denominator independently. So, the denominator turns out to be 1 differentiating with respect to h for which we are taking the limit. So, denominator becomes 1 and the numerator f of a is a number. So, that gives 0, it is just f prime of a plus h. Now, here if you substitute h equal to 0, you would get back that f prime a. Similarly, in the previous case also x square plus x minus 2 divided by x minus 1, if you differentiate the numerator, so that gives 2x plus 1 on the numerator and denominator is minus 1 becomes 0 after differentiation, x gives 1. So, it is 2x plus 1 by 1, which when you take limit x goes to 1 gives you 3 again, that matches with the earlier answer. So, in both the cases we see that if it is in the 0 by 0 form, you differentiate the numerator, differentiate the denominator, then take the limit. answer turns out to be the same. That is exactly what we want to justify, right. So, to justify this, we will prove a slight generalization of our mean value theorem, that will be useful. So, this is the generalization which is called Cauchy mean value theorem. So, here our assumption is that there are two functions f x and g x which are continuous on the closed interval a b and differentiable on the open interval a b, just like in mean value theorem. In mean value theorem, we have only one function. Now, we have two functions. Now, suppose g prime x is not equal to 0 on the whole of the interval a b, that is, it is non-zero at every point in a b. Then the theorem says that there exists some number between a and b such that if you take this ratio f b minus f a by g b minus g a, that will be equal to f prime c divided by g prime c. Now, why is it a generalization of mean value theorem? Well, in the mean value theorem, you have f prime c equal to f b minus f a divided by b minus a. So, it suggests that we take g of x equal to x itself. So, if g of x equal to x, the identity function, it satisfies this condition, g x which is x is continuous on the closed interval a b, differentiable on the open interval a b. So, there exists a point c such that f prime c divided by g prime c, which is now derivative of x evaluated at c, but derivative of x is 1. So, even at c is also equal to 1. So, on the left side you get f prime c, on the right side you get f b minus f a divided by b minus a, as the mean value theorem we have stated earlier. So, first we will prove this generalization or Cauchy mean value theorem. So, the proof is simple. First thing is, observe that we are writing g b minus g a in the denominator. So, it should not be 0, but we have not assumed that anywhere. Well, we have not assumed because it can be derived from there, from the conditions given. So, how is it so? Suppose g b minus g a equal to 0. On the contrary, assume that g b minus g a equal to 0. Now, you can apply Rolle's theorem or by mean value theorem. So, that will give g prime is equal to 0 at some point between a and b, g prime d equal to 0 for some d in open interval a b. But that will contradict our assumption that g prime x is not equal to 0 on the open interval a b. Therefore, g b minus g a can never be equal to 0. So, this right side quantity f b minus f a by g b minus g a is well defined. Well, so g b minus g a is not equal to 0, that is what we conclude. Then what we do, here is a little trick, just like in mean value theorem, we define a new function h on the closed interval a b to the real numbers. So, what is the definition? At any x in closed interval a b, h of x is equal to f of x minus f of a minus f of b minus f of a divided by g b minus g of a, which is non-zero we know. So, we can divide now, multiplied by g x minus g a. So, this one is a number, this is also a number, everywhere else x is there. Okay. So, that is how h is defined. Now, what properties h satisfy? First thing is f and g both are continuous on the closed interval a b. So, this is just f x minus a constant times g x plus another constant, right. So, that is also continuous on the whole interval closed interval a b. Now, similarly differentiability, both f x and g x are differentiable on the open interval a b. So, h of x is also differentiable on the open interval a b. Next, you see what is h of a. Suppose I take h of a, you substitute x equal to a. So, this is f of a minus f of a, which is 0, and here again g of a minus g of a, that is also 0. So, that is why h of a equal to 0. And what about h of b? Well, if you take h of b, it is f of b minus f of a, and this side g of b minus g of a cancels with denominator g b minus g a. So, you get f b minus f a minus f b minus f a, that is also equal to 0. So, you see that h a equal to h b equal to 0. We do not need of course equal to 0, at least h of a equal to h b. then you can use Rolle's theorem. So, Rolle's theorem says that there exists a point C between A and B such that h prime C equal to 0. Now, what is h prime C? F of A becomes 0, a constant. So, this gives f prime x, that gives f prime x evaluated at C, minus you have f of B minus f of A divided by g of B minus g of A, and the quantity is g x minus g A, its differentiation is just g prime, g A becomes 0 in the differentiation. So, it is g prime of x evaluated at C. So, that gives g prime at C. So, we have one C in a B, this C such that h prime C equal to 0. So, once this quantity, this is h prime C equal to 0, it gives your conclusion that a prime C by g prime C equal to f b minus f a by g b minus g a. So, it is a simple proof, and the proof follows the same line as mean value theorem by defining a suitable function h. Okay. So, the main thing here is from the mean value theorem, this is that suppose you apply mean value theorem independently on f and independently on g, then you would get f prime C equal to f b minus f a by b minus a, and similarly g prime of d will be equal to g b minus g a by b minus a. For the right side, there exists one d such that, similarly there exists C such that. So, that means you would have got the ratio f b minus f a by g b minus g a equal to f prime C divided by g prime d. We do not know whether these C and D are equal or not, but the potency of this theorem, this result is that you can choose a point C where both the things coincide, both the things can be evaluated at that C. You do not have to take two different points C and D. That is how this theorem says something more than the mean value theorem. Okay, we will see how to apply this for proving L'Hopital's rule. So, L'Hopital's rule says that suppose f x and g x are two differentiable functions, and differentiable where? In a neighborhood of A. So, A is a point, we assume that there exists some delta greater than 0 such that in the open interval A minus delta to A plus delta, both f x and g x are differentiable. Now, at A, suppose f of A equal to g of A equal to 0, that is our ratio, right. We cannot substitute x equal to A, we are telling. So, suppose both of them are 0. We are interested in limits of this kind where f of A and g of A both are 0 when you substitute x by A. So, that is one of our assumptions, and we also assume that g never vanishes in the deleted neighborhood of A, that is at A it is equal to 0, but except that nowhere else in the open interval g is 0. Similarly, g prime is also not 0 in the same deleted neighborhood, whatever delta we have taken there. Okay. So, these are the two basic assumptions. Then what the conclusion is? Conclusion says, if you take limit of x goes to a f prime x by g prime x derivatives, and then what will happen? If this limit exists, then limit of f x by g x also exists, and the limit value will be equal to the limit value of f prime x by g prime x. Okay. So, this is the conclusion, which means if you do not know whether f x by g x exists or not, you can compute f prime x, you can compute g prime x, find this limit. If this limit exists, then that will be equal to the earlier limit of f x by g x, and that f x by g x also exists. Both the things come from there. But these conditions are crucial. We should have it is in 0 by 0 form, so to say f of A by g of A, that is in 0 by 0 form, and the downside that g x never vanishes in the deleted neighborhood, neither that vanishes nor its derivative vanishes. These are the two conditions under which the conclusion holds. Okay, proof is very easy, right, because all that you have to do is go back to our Cauchy mean value theorem. We will be doing that slowly. Now, what we do? We will come back to this after that proof again, that will be easier to see. So, let us prove L'Hopital's rule. Now, suppose x is any point inside a to a plus delta. Let us consider first one sided limits, that will also be helpful later. Now, suppose you take any x between a to a plus delta, that is x is bigger than a, but smaller than a plus delta. Now, both f and g are continuous on this closed interval a to x, that is our assumption, right. It is continuous there, it is differentiable there and so on, and it is differentiable on a to x. Now, g prime is not equal to 0 on a to x, that is also one of the assumptions. So, by Cauchy mean value theorem, there exists a point theta between a and x such that f prime of theta by g prime of theta equal to f of x minus f of a divided by g x minus g of a, and we know that f of a equal to g of a equal to 0. So, that is same thing as f x by g x. Now, we are interested in the limit of f x by g x. So, as x goes near a, it approaches a. Now, theta is in between x and a. So, theta also approaches a. Therefore, limit theta goes to a plus of the left side equal to limit x goes to a plus the right side, f x by g x. Okay. So, you see here that we have really proved the theorem, but only for the one sided limit x goes to a plus. So, it is f prime theta by g prime theta, theta goes to a plus is same thing as f prime of x, g prime by x, x goes to a plus. Now, if it is in the other side, that is left side limit we are taking. So, we take any point t in a minus delta to a. Then in that interval, that is t to a, we find that similar concern, that there exists one tau between a minus delta to a, between t to a, not a minus here, between the in the open interval t to a, there exists some tau such that f x minus f a by g x minus g a, or you can write t here, f of t minus f of a divided by g of t minus g of a is equal to f prime tau divided by g prime tau. Okay. Now, f of a g of a equal to 0. So, that goes away, you get f of t by g of t. Now, again as t goes to a, tau also goes to a. So, limit tau goes to a minus f prime tau over g prime tau equal to limit t goes to a minus f t by g t, which we can write in terms of x also, both the things. So, that means the similar way as the right sided limit behaves, the left sided limit also behaves the same way. And since our assumption is f prime x by g prime x limit x goes to a exists, both these limits are same, right sided limit and left side limits. So, this on the right hand side of the equality, both these right side and left side limits are same. Therefore, limit f x by g x exists, and this is equal to that limit. But you see here something else also that completes the proof, of course. Even one sided limits also hold true, the similar things for the one sided limits. So, that means suppose I have the interval a to infinity and we want to find limit x goes to infinity, then there only left side limit will be useful, then this one will help us. So, a similar thing also holds for indeterminate forms of the form plus or minus infinity by plus or minus infinity, or plus or minus infinity into 0, or infinity minus infinity, because there you will be concerned with one sided limits. Okay. Fine. Even x goes to infinity or x goes to minus infinity, similar things also can hold. That is what our observation says. Okay. So, let us take some examples where we can apply this. Let us take first limit x goes to 0, square root of 1 plus x minus 1 minus x by 2 divided by x square. So, as x goes to 0, its numerator is square root of 1 minus 1. So, that also 0, and x square is of course goes to 0. So, it is in 0 by 0 form. And you can see the other things, your f x is on the top. So, it is continuous or differentiable, should be in a neighborhood of 0. right, and that is true. You can take a neighborhood which is delta should be smaller than 1. So, that 1 plus x square root can be well defined to the left side also, right. So, by taking a suitable neighborhood, we see that all the assumptions of L'Hopital's rule are satisfied. Therefore, we say that this limit, if exists, will be equal to the next limit, where we can differentiate the numerator and denominator independently. So, we will just write this limit is equal to this, but it is conditional. Remember this, it does not say that the limit exists and this is equal to this, it says the other way. If the second limit exists, then the first limit is also exists and they are equal. That is what this equality symbol says. Okay. So, keeping that in mind, we write such equations that limit is equal to this limit. So, differentiation of the numerator is 1 plus x to the power half, that gives a half times 1 plus x to the power minus half, and differentiation of 1 is 0, differentiation of x by 2 is half, keeping that minus sign as it is. So, that is the differentiation of the numerator, and denominator gives 2x for x square. Now, if can I substitute x equal to 0 here to get the limit? If you substitute, you will get 1 by 2 into 1 minus 1 by 2, that is 0 on the numerator, on the denominator also it is 0. So, again it is in the 0 by 0 form, right. So, we apply again L'Hopital's rule, say that this limit exists provided the next limit exists, which will be limit x goes to 0, differentiation of the numerator by differentiation of the denominator. So, now we will write this is equal to limit x goes to 0 and we differentiate that. So, this is half into minus half, that is minus 1 by 4 into 1 plus x to the power minus half minus 1, which is minus 3 by 2, divided by denominator is 2. Okay. So, now we can see that the limit can be expressed where denominator is not 0, right. So, when x goes to 0, 1 plus x goes to 1 and power is minus 3 by 2 there. So, it is minus 1 by 4 divided by 2. So, this is giving you 1 by 8, right. This is really minus 1 by 4 into 1 to the power minus 3 by 2, and so this is 3 by 2, there is a negative sign, right. So, that should be minus 1 by 8. This gives us 1 and there is another 2 of course 1 by 2. So, that gives you minus 1 by 8.